Hello everyone, welcome to this lecture series of engineering mechanics, and in this lecture we are discussing the dynamics aspect of mechanics, and in which we will be discussing about energy methods, and we will see how the energy methods will be used in solving the dynamics problem. So energy methods actually includes the majorly the kinetic energy and the potential energy along with the work done. They are also one type of work. Kinetic energy is also one form of work experienced by the body when it's moving, and the potential energy is also one kind of a work which is experienced by the body when it is at certain height above the ground level. So the body actually absorbs the potential of the energy. Um, we know till now that we are discussing all this due to the aim of Newton's second law of motion. We have solved the earlier some of the dynamics problem using this law. However, in this chapter, we will be discussing the work and the energy methods. And the approach is very simple actually. Um, the forces and the accelerations used are um, are used to develop the equation of motion, and similarly the velocities and displacements are obtained can also be obtained by the work energy method. And later on in the next lecture we'll be discussing time histories in which we will see how the impulse momentum equation will be used in solving dynamics problem. So this is the basic equation in which the kinetic energy of the um, initially what is the kinetic energy of the body accompanied with the work done by the body is equal to the kinetic energy of the body after the work has been done. Like for example, if the body is here, okay, and the force is applied on this body, so initially its kinetic energy is zero because it's not moving, okay, and after the work has been done, the work done is u1 to 2. That means from location 1 to location 2 the body moves at some distance, so work done will be there, and accompanied with these two we will be having the new kinetic energy T2. So if the initial position is at rest, we'll take the initial kinetic energy as 0. If the body is moving initially, then the kinetic energy will be there along with the work done. So this is actually one position to another position. So this is one position and this is another position of the body. So what will be the amount of work done accompanied with the kinetic energy will be equal to the new or the updated kinetic energy of the body. So we'll see this, but before that let's define the work. So this has been already defined many times in our previous lecture. What exactly is a work? Work is done when a particle or a body moves to a certain distance and to a new location. So A is or a body at A moves to a new location A dash, and the force is applied on this body with the help of this force. So what will be the work done? Since this force is not along the line of action, so we'll take the component along this line of action, which will be cos alpha. So the work done will be cos alpha times the distance. Distance is dr. So the magnitude of dr will be ds. We used to write the magnitude as ds. Okay. So the work done will be F times dr, the dot product, and this is F ds cos alpha. Okay, magnitude times cos alpha, the component in the traveling direction. And this further can be represented um, in terms of rectangular coordinate systems. And remember that here fx is a magnitude and dx is also a magnitude like ds here, and ds is a unit magnitude along the x direction. In a similar way, dy is the unit magnitude, along the y direction and along the z direction respectively. Okay. Work is a scalar quantity, we know that. It has a magnitude but it does not have a direction. And work is usually related or usually measured in joules, which is 1 Newton meter. Okay. Work can also be defined when it is traveling on a path. Like in this case, the body moves from point A1 to point A2. So when moving on a path, so we need to integrate the overall path, the work done on the path. We have to integrate that. So work done will be from position 1 to 2 will be integration from 1 to 2. That requires the dot product times the integral from 1 to 2. So FDR is F cos alpha ds and S1 to S2. As I said, ds will be the magnitude. In a similar way, S1 to S2 will be the path. So this will be like this only. Remember that Ft here represents F cos alpha. That means the tangential force on this path. Okay. And similarly, this can be further divided in the rectangular coordinate systems where Fx dx will be the component along the magnitude of the component along the x direction, y direction and z direction respectively. So majorly if you analyze this, so work done will be force times the distance moving in that particular direction. Remember that it will be a distance moved in that particular direction. Whatever will be the orientation of the force, that does not matter. We have to take the orientation or the component of that force in the traveling direction. Okay. So along with that, if we draw a diagram of force versus displacement, okay, we'll be having such type of trapezium, and work done will be the area under this curve, and this curve will be having the absolute S1 to S2 and the Ft will be the work done. Ft will be the force acting on that body, particular body. So as you can see here, the Ft is changing the component of Ft is changing on this path, because the component is changing, the tangential component is changing with respect to alpha on this path. Okay. On this path the component is changing, the force is also changing. Now what is the work of a constant? This is a small question. What is the work of a constant force in a rectilinear motion? That means motion along a line. So what will the force of work with respect to these four terms? So the force of the work will be F cos alpha in this direction times the distance. So F cos alpha times the distance, not sin alpha. This is cos alpha. Okay. So this will be the answer. Correct. Then the force of the work on a path. Again, the path will be initially at y1, then to y2. So we'll integrate that and we'll find out the work done. W is the weight of that work. Remember that here the force is W. The force is trying to keep this body in this direction. So work done will be negative. Why? Because we have to calculate the work done from here to here. If you calculate the work done from here to here, this will be negative because this is a slope. This body is moving in this direction. So work done will be positive in this direction, negative in the against direction. So that's why it is negative, because we are calculating work done in the against direction. So these are the small things that you need to remember before doing that. Okay. So further, work can also be done on a spring. So we have seen in many of the practical examples of a spring, and this is one body which is being which is extending this spring. So after the extension of x1, the spring moves to a new location. So remember, when the spring is extended, there will be a tension force existing on this spring. The distance has been moved to a new location, and in this case the new location is this A2. So from A1 to A2. So the energy absorbed, remember that whenever the spring is stretched, this is stretching of the spring. the energy absorbed will be negative, because you have to give the energy to extend the spring. So in that case, the energy will be negative. If you release the spring, the energy is dissipated. That means the energy is positive. So always remember this concept, and this will be shown in this also. Work of the force exerted by this spring. So the force is in this direction because there is a tension force trying to make the body go in this direction. However, there is some force, though that force is not shown here, but there is some force that is keeping this body stretching. So the work done will be negative times Ks. The spring is expressed in this form. We have already discussed that the force is equal to, the force is actually proportional to the distance. The more force I will apply, the more stretch will be there. So K is the constant of the spring. This depends upon how elastic the spring is. There are different types of springs. Some are less elastic, some are more elastic. This is a spring constant K, and this usually is given to you. So the work of the force is du minus f dx minus k. So what will be the work done? This is the elemental work done. So what will be the work done? Overall work done will be integration from x1 to x2. This is the initial position, this is the new position. So work done will be from x1 to x2. Half x1 square minus half x kx2 square. This will be the work done. Overall work done will be negative because the spring is stretched. If the spring has been released, the same expression will be there. However, this will be positive in sign. Okay, the same thing that I have explained. Now let's solve a small problem. The spring is undeformed, and after certain location, the spring has been deformed to a new location. So as the block moves from A0 to A1, is the work is positive or negative? It will be negative. We have just now seen. And if the block moves from A2 to A1, that means the energy is released. The spring energy is released. So in that case, the work is positive, definitely. Okay. In this case, there is no spring here. So does the normal force do the work as the block slides from B to A? Does the normal force do the work? This is the normal force of this spring, of this block, and this block is sliding. There is no normal force that actually used to do work. Okay, the work has not been done by the normal force. Normal force usually do not do work because there is no expression here. The block is just sliding down in a fashion. So the energy is released here. Okay, so this is a kind of a positive energy. So no work is to be done by the normal forces. Does the weight do work as the block slide? Yes. The weight of the block is actually the force that is driving along this inclination. That is why the higher objects will be going through larger momentum. So that is actually correct. What should be the work, positive or negative? I have just now told you it should be a positive work because this is releasing the energy. This is going in a downward direction, usually towards the gravity, towards the earth. So this is positive. If it would have been going in the inclination, it would require a work to do, because we need a work to do to make this body go from here to here. However, no external forces are required to move this body from here to here. Only the weight of the body can do that. So forces which do not actually do work are the reaction forces, or reaction at the frictionless surfaces, or further reaction at a roller moving along its track, or weight of the body itself when it is at a center of gravity. Now let's define a kinetic energy. We have earlier seen what is the work done. Now we will see what is the kinetic energy of the body. Now from the Newton's second law, we know that the tangential force is one of the component that is driving this block from A1 to A2. We can write this as this Ft equals to MAT. AT can be written as dV by dt, and using the chain rule we can write M dV by ds, ds by dt. We can write momentum mv times dV by ds. We can take the ds here and write the equation in this form, and further we can integrate this from A1 to A2. Once we will do that, we will be obtaining work done from position 1 to position 2 will be equal to change in the kinetic energy of the body. And this is something that you already know. There is nothing new here. The work done from the body from point A to point B will be change in its kinetic energy. The kinetic energy at location T2, location A2 will be T2, and this is T1. So the work done will be change in the kinetic energy. I can write the expression like we have already seen. That expression was written in this form. In this form, T1 plus U1 to 2 equals to T2. That means initially the body was at certain location, and after the force was applied, the body came down to another location, T2. So here, what will be the original kinetic energy of the body? That plus the work done from moving this body from here to here. That will work done will be U1 2. So this plus this will be equal to the kinetic energy at this location T2. That's the equation we need to remember. This will be used frequently in different problems. Okay. So this is also one kind of a simple problem of a simple pendulum, in which we have a bob which is striking here, which is at this location. Initial kinetic energy is 0. What will be the overall velocity at this location? That we are finding. So T1 is 0. So U12 times will be equal to T2. Okay, you can check it out. This is very easy by using Newton's second law of motion. We have calculated it simply. It's very easy actually. Further, we'll see one kind of a problem in which we have an automobile which is weighing 4000 lb, 4000 pounds, driven at a 5-degree angle. So this is descending actually. This is descending. This is with the this is not against the gravity, this is with the gravity. Inclination at a speed of, this is the velocity. So the initial T1 is this. When the brakes are applied, causing a constant total braking force to be this. Okay, so once the brake will be applied, this is the new location, this is, let's say, location 1, and this is location 2. So this was the brake applied during that path. So the work done will be from here to here, initial kinetic energy, and this will be the total kinetic energy, and the work done is by the brakes. So U12 will be calculated based on the applied brakes, and this is the braking force. Okay, force that is braking. Determine the distance traveled by the automobile before it stops. So we have to find this distance. Okay, how much distance is traveled? Let's say this is x. So we will have the equation T1 plus this force times 1500 times x will be equal to T2. Simple equation. So you can expand this and write this, how this is done. This is velocity V1. We calculate T1. T1 comes out to be this. So we'll be having a T1. Now since the vehicle comes down to rest, so the velocity T2 is 0. Since the velocity T2 is 0, that means velocity V2 is 0, so that means kinetic energy is also 0. The T2 is 0 because the vehicle comes down to rest. That's why the velocity is 0. So we have only one thing left, work done, to determine that. So work done will be that load 1500 times x, and remember that since it is descending, okay, this work is descending, this is with this direction, that's why the work done will be in the negative. So this is 1500 times x plus the work done by this component of the weight of the car. So work done will also be by this component of the weight of the car, which is 400 lb times sine x, because this is the component, times x. Okay, so x is constant here, the distance, we have to find the distance. We will put this in this equation and we'll find it out, the x comes out to be that much amount. So this looks out to be a very kind of a simple problem. Remember that once it is descending, the work done here is this is the descending work done due to this weight of the car, and this is a braking force. That means this is actually the frictional force, or the friction caused by the brakes on the tire. Since this is a friction force, this is resisting the motion, so this will be, the work done will be negative since this is resisting. And the work done by the weight of this car, W, component of this W will be, the component of this will be here, 5-degree angle, so this will be positive. Okay, because this is along the direction, or with the direction of the car. So that's why it is negative here, because this is a braking force and this is positive. So in this way we will calculate the distance. This is another problem in which two blocks are joined by inextensible cable. That means there is no extension of this cable during the movement. If the system is released from rest, determine the velocity. That means release from rest means velocity v1 is 0, and that means t1 is 0. To determine the velocity of the block after it has moved 2 meter distance. So distance has been given to us and force has been given to us, the weight of the block that will move or do the work times distance. Assume that the coefficient of friction is this, that means the friction force will also include or actually reduce the work. When the work has been done by this block, this friction force will also be there and this will reduce the work. Okay, and the pulley is weightless. Okay, so we have to find the coefficient of friction. What is the coefficient of friction? So let's see how this is solved. So first of all, the weight of the block, which is mass times acceleration. This is the weight actually. And what will be the friction force? Nu k times the normal. So if this is W, this will also be same, the normal. So normal will be W only. This is the friction force. Okay, now we have this equation. So the initial velocity is 0 plus what will be this? Fc. Fc will be the moving velocity, moving force times 2 meter. Now I don't know the moving force. I know only the weight. I do not know the moving force. However, I know the friction force. Matlab, I do not know the friction force also, but I know that the friction force will be negative because it will be against the direction of the work. It will reduce the work. So that is what it is reducing. It's reducing the work done by the force Fc times or equals to half ma v square. That means the final position of the block. So we'll write each and everything in this fashion and we will solve this. So this is one equation for this. The another equation for this coming from this block B. So what will be B? B will be having the same force Fc. The same force will be there. See, because this cord is inextensible, it will not stretch. So the force applying on this cord or tension applying on this cord will be same as this. Okay. So Fc will be, and what weight of the block will be there. So Fc here is negative because this is trying to reduce the work done by this block WB. The same Fc is positive here because this is along the line of direction or along the work done. Okay, and in this WB is towards the gravity, so this will be positive times W. This is the work done, and this is 0 because the initial velocity is 0 times this. So we have two equations. So we'll solve for velocity. and we have solved for the velocity. Velocity comes out to be 4.43 meter per second. This is the velocity of this A, the velocity with which it is moving. And remember that since the velocity of this and this, it is connected with a string which is unstretchable, so the velocity will be same for both the blocks. Now a twist is there. Can you apply work energy method to combine the system of the blocks? What is T1 of the system? So the T1 is 0, and what will be the total work done from point 1 to 2? The total work done will be friction times W times distance. So this is work done by the friction, which will be against, and then work done by this block. So this is another way of calculating what will be the work done by the T2 system. T2 system you can obtain in a similar fashion. Okay, we can solve for the velocity, and this is the kind of an alternative way of solving the same problem. Then comes up to another problem. This is also a very interesting problem. In this there is this is a package which is moving with a velocity of initial velocity of 2.5 meter per second. The weight is 60 kgs, and this will go in this direction and hit this spring, and since it will hit the spring will compress. Okay, the spring constant is given, and initially it is compressed to, that is the maximum compression, 120. The package has the velocity, maximum deflection of the spring is 40. These all things are given. Find the coefficient of kinetic friction between the package and the surface. That means nu k you have to find. Okay, one thing. Another thing, velocity of the package as it passes through the position shown. Velocity of the package, that means at this location what will be the velocity, what will be the coming of velocity, sorry, velocity of the package as it passes again through the position shown. What will be the rebound velocity here? So that is what we need to find it out, the coefficient of friction. So again we'll draw the diagrams. So the velocity v1, it is hitting with a v1, and v2, that means at this location it has exhausted all its velocity and giving all the energy to the spring, due to which the spring has compressed. So initial velocity is this much, and the another or the final, the initial velocity is given, due to which the kinetic energy or the initial kinetic energy is this one. And what will be the what will be the final kinetic energy? T2, because all the energy has been given to the spring, and due to which the spring actually compressed. That is the 2 location at point 2 where the spring is completely compressed. Now we will have to find out the work done, because the T1 is known, T2 is known. The work done will be important. Now the work done first of all is to be done by the friction component between the two surfaces. The work done is negative for the friction, minus nu k times Wx. W is the weight of this block times the distance. So the distance is 600 mm. This is put here and the equation is made. Now the work done by the spring. Remember that the initial or the minimum P, the pressure here, or the force, is kx naught, the initial position of the spring. So here the initial or the previous energy was this, or the previous force was this, and the maximum force that the spring can actually sustain is this. How much is this? 0.120, that means 120 mm plus 40 mm. 40 mm is given. The compression limit of the spring is given. See, maximum deflection is 40 mm. So this is given. So we'll add, and what is the initial compression? 120 mm. So we'll add 120 plus 40. So that is what the new force of the spring, or maximum force of the spring at one. So we'll add up to, and we'll integrate, or this is, since both of this has been calculated separately, this one and this one, we'll multiply it with the delta x and we'll find out the energy. And here the energy is negative. The spring energy is negative. Why it is negative? Because the spring is compressed. It absorbs energy. The compression of the spring means it absorbs energy, and that is negative. When the spring releases, it releases the energy, and the energy is in positive. So the overall energy will be friction and this. So we have this equation. We'll put it in our usual equation and we'll find out the coefficient of friction. Very easy. Now what will be the new velocity? Okay, you have to find out the new velocity of the block. When it releases the energy, it will hit on this block again, and this block will move with some velocity. What will be that velocity? So we will make another system. T2 here is 0, and because the velocity becomes 0, and then what will be the new kinetic energy? The energy with which the spring actually hits back will be with this new velocity. So 2 to 3, this is 2, and this will be another new location 3. Okay, this will be location 1. So it goes from 1 to 2 and 2 to 3. So 2 to 3 will be, again the friction will be offered 2 to 3, that amount plus 2 to 3 the spring release. So everything remains same. The friction will, though the friction will now act in this direction. Earlier the friction was acting in this direction, but the work done by the friction will always be negative. Will always be negative. However, the work done by the spring now will be positive because the energy has been released. The same energy has been released, which was actually absorbed earlier. So now this will become positive, and we will put this in the same equation and we will solve this for V3. We'll get the new position of the block. This is how these problems should be addressed. This problem should be solved. A new problem came. This is another problem in which we have a path. We have a path from where this person is going from path 1 to 2 and 2 to 3. This is somewhat you have seen in the roller coaster rides also, where such type of ride actually happens, or something during the ice skating from 1 to location 2 and location 3. So this is the load of this person or this car is this much pounds to 2000 pounds, and it moves from rest. So this is rest. Is moving from rest. That means T1 is 0 because velocity is 0. Okay. Moves without friction. So we will not consider friction. Work done by the friction we will not consider. Determine the force required by the track on the car at point 2. What will be the force required exerted by the track on the car at point 2? That means we have to find the normal force. This is what it is written. Force exerted by the track on the car at point 2. That means the normal force. And what will be the minimum safe value of the radius of curvature at point 3? So we'll find it out by using the work energy principle. So we'll apply the work energy principle in which T1 is 0. What will be T2? It is given half mv square. Velocity is not known till now. So this will be like this. This is mass. W by g is mass. Now what will be the work done? Work done will be W, the weight of this, times the distance, 40 feet will be the work done. Put it in this equation. Very simply obtain this and calculate the velocity. Simple, as simple as that. Now what will be the new location? The new location is point 3. So once he will come here, he will then move towards the location 3. And at location 3 we actually have to find the minimum safe value of the radius of curvature at point 3. So we will use Newton's second law of motion to find the normal force at the track point. So first we have to find the normal force here also. So what will be the normal force? So overall force, the normal force will be minus W because the W is in this direction, plus N minus W plus N. They will be same, will be equal to MAN, mass times acceleration. This is what our equation is, the normal component. We'll put the values and this comes out to be 5 times the this comes out to be almost 1/5 times the weight of the car or the person. So the weight of the car was actually it was, what was the weight of the car? So it was this much, and that's why it has now calculated as 1000 lb, 10,000 lb. Okay, so we will move forward, apply the principle of work and energy to determine the velocity at point 3. So at point 3 we will use this equation T1 one location and T3, and what will be the overall work done from point 1 to 3. Initial is 0, work done from 1 to 3 is W times 25, 25, 40 minus 15 is 25, half mass times velocity. So this will be V3. So we'll find out the velocity as 40.1 feet per second. Now what will be the radius of curvature? Now to find out the radius of curvature, we will using the Newton's second law of motion. Newton's second law of motion. Why we are using the Newton's second law of motion? Because with the help of Newton's second law of motion only, we can find the normal component. Why? Because the Newton's second law of motion, with the help of this an, actually we know that the tangential component is tangent to this and the normal component is along this. Okay, so we need to find the radius of curvature r, and that is obtained, this is rho actually, r or rho. So the radius of curvature will be obtained only through an, which has the formula v by rho, sorry, v square by rho. So we'll use that and obtain the radius of curvature. And remember that this is the minimum radius of curvature that is required, so that the overall normal force should be approximately 0. This will be the overall normal force. So that means there will be no normal force applied on this ground, on this car, the car that is moving, because if the normal force would be somewhat greater than 0 or anything greater than 0, then this person will come here and it will be kind of flying from here. It will fly. And why it will fly? Due to the action of the normal force. The normal force will not make it keep it on the ground, and it will push it upwards. So this much amount of radius of this curvature is required so that he will land safely at point 3. I hope this is clear to you. Any queries can be addressed afterwards. We will try to solve another problem. So we are solving a lot of problems here so that you becomes comfortable in in different problems. So solve another problem, and in this problem these packets are being dropped. This mostly happens during the transportation when there is a luggage loading on the conveyor belt or in the trucks, automated trucks that actually loads the conveyor belts. So this happen actually. They are being dropped from a certain location and they use the advantage of the inclination, and the blocks goes there and actually jumps towards the conveyor belt, and then it will be having some small velocity. So initially it may be given some velocity, but apart from this it will regain its velocity due to the inclination offered by this inclined. So inclination, and due to its weight it will gain some velocity, accelerate itself, and then it's come down, decline in some velocity will be there, and then it will shift from this new conveyor belt. So what is to be done? So the package slides along the surface to a conveyor belt, and conveyor belt has a movement of 2 meter per second. Friction is known, so we'll be countering the friction in this direction between the package and the surface. To determine the distance if the package has to arrive at a velocity of 2 meter per second. So in this problem, we will deal with this problem with the position changes and different velocities. So we'll use work energy principle. So let's define things. Initially, the velocity is 1 meter per second. At point C, we have a velocity of 2 meter per second. And find the distance. Distance is d here. So what will be the equation? dA plus UAB, this energy from moving this package from A to B, and energy required moving from this package from B to C is equal to location C. So TA will be calculated based on 1 meter per second, TC will be calculated based on 2 meter per second. Let's calculate these work dones, AB and BC. Let's calculate AB. So let's see this FBD, basic FBD. W is the work done, NAB will be the normal, and this is the friction force. So normal force will be mg cos 30 degree, that will be the component, and FAB is the friction force, that will be against the direction of the motion. So this will be negative, friction force is subtracted from mgd sine theta, so we'll be obtaining this expression. Now what will the work done from B to C? From B to C, you have you have understood this, na? From A to B, why this is done? mgd cos, so this is mgd, normal is mgd this 30 degree, and this is w, mg sine 30 degree, w component times the distance. This is basically the distance component. So this will be cos 30 degree, and what will be this? This will be d times mg sine 30 degree. This will. Okay. So this is weight times this distance minus the friction force FAB times the distance d. So this is how this is written. What is work done from B to C? The normal will be here NBC at this location. Okay. And this distance is 7 meters. Friction force is also there, nu k this. So we'll be having simply nu k mg xbc, which is 7 meters. So we have these two equations. We'll put them in the above one, and we will find out the values. So we'll solve this and we'll find out the distance d required here. Okay. This looks to be something that needs to be done using calculations, but the concept here, we are actually discussing the concept, and if anything is important in the problem, I specifically mentions that, specifically makes you understand that, and we actually specifically talks about that. Anything important, rest of the things are only calculation. You can do it by yourself also. This is very simple. Okay, so let's move forward. Now if you wanted to bring the package to a complete stop at the bottom of the ramp, would it be a place to where would it be a place to place a where would a place where the spring should be placed? Okay, no, because the potential energy of spring would turn it into kinetic energy and push the block back up to the ramp. So even if you place any spring here so that the movement of this is stopped, this will not be possible because the spring will absorb the energy and throw it back. So it will actually goes back here and maybe gets damaged. So it will not comes to a complete stop at once. Would the package ever come to a stop? Yes, it will, when its full energy will be dissipated after the friction offered by this surface. Once it will hit it, it will go back, come back, go back, and then after some time when there will be a friction, so it will energy will be dissipated, it will come back to its still position or stop position. Now as we have said, there is a kinetic energy which is based on the movement of the body or the velocity of the body. Another way is to define the energy is the potential energy, which is actually stored in the body when you raise a body to a certain height, and this energy is actually as a effect of gravitational pull from the earth. So the potential energy is stored, like in this example, in a roller coaster. This is the movement here actually is done by the potential energy, because this is kind of a free fall. So they actually have to apply the brake to counter the potential energy. They are applying the brakes also, and there will be a friction also. So all these forces will be there, so that the potential energy is countered, and these all people and the roller coaster comes down in a controlled fashion. Okay. This is another example of a girl um, um, jumping on a trampoline, and this is some children used to do that. Nowadays this is available almost everywhere, in shopping malls, besides shopping malls where students can play, and in students playgrounds also. And this is some kind of elastic cloth on which the people used to, or these children used to bounce. And what will happen, the elastic potential energy stored in this tempoline is transferred to the kinetic energy and gravitational pull upwards, due to which this girl goes upwards. So this elastic potential energy is converted into the kinetic energy, due to which it goes upwards. And then from the gravitational pull, it will come back downwards, go upwards, and come back downwards, and this process will continue till the time she is exhausted. Okay. So this is how the energy is getting converted from one form to another form. And you all know that the energy is conserved. It will not be destroyed. It's always conserved. So sum of all the potential energies and kinetic energies, all sum will be equal to constant. So, and this is something very important. If the work done of the force depends on the differences in the position, and that is the potential energy. So which are these forces actually offers the potential energy? Weight offer the potential energy? Definitely. Friction, no. Friction does not offer any potential energy. Normal force, no. Normal force is applied here on the, it's a kind of a reaction, and we have seen that the reaction forces does not offer any kinetic or potential energies. And what about the spring force? The spring force actually absorbs the energy, and that absorption is actually a potential energy or only. Always remember that since we have discussed the springs earlier as well, the energy stored in the springs are always potential energy. It's not kinetic energy. Although we have discussed this in the kinetic energy section, but remember that spring force is always a potential energy stored inside the body. Although, okay, so spring force will always stores a potential energy for you. It will not move from any location to any location. It will only traverse some distance. The spring is stretched or it will compress, and all it will store is potential energy, not kinetic energy. Though the work done by even by potential energy or by kinetic energy will be same, because that is only the work done. It doesn't matter it's a potential energy or a kinetic energy. It is a work done, and that is what we are doing in our expressions. T1, the initial kinetic energy, plus the work done by the spring or by the any other thing will be equal to T2, the kinetic energy. So we are actually adding up the through the work done, although that's actually a potential energy. We'll discuss about the potential energy, and the potential energy goes with respect to the gravity. So the work done from 1 to 2 will be W times Y1 minus W by 2. Okay, and this is equal to Wy, and remember that W is equal to mg. So this is actually mgh, the same thing that you have known. Mgh, W is mg times y is actually the distance I am taking from the datum. So you have to first of all in your problems define the datum. So this is the datum position that you are defining. times the mg. So mg may be h or y, the whatever way you actually defines. So the work done will be the change in the potential energy from one location to another location. That is the change in the potential energy is actually the work done. And something similar happens in the kinetic energy also. From position 1 to 2, actually the change in the positions defines the kinetic energy also. So the things remain same, only the potential energy has came instead of a kinetic energy. Although the work done by them is same, the units are same, all are defined in joules. Okay, they are also in joules, they are same. And the spring, I have already told you that this is due to the potential of the spring constant, and this is what it should becomes in potential energy only. And this is the potential energy half kx square, and this is the work done. This is the deformed position minus undeformed. This is the undeformed position minus the deformed position. So, and this is the work done, work conservation of the work u1 to 2 equals to v1 minus v2, and u1 to 2 is t2 minus t2. Kinetic energy and potential energy of the bodies are always conserved. It may change from kinetic to potential, potential energy to kinetic energy. However, the sum of all of them will always be constant. And this is what it is written in this form. That the initially, if there is a body, like for example a football, and you are kicking this football, though this is not round, sorry, this is a football, and you are pressing this force on this football, pressing your toe, then it will move and go at some other location. So it will be having T1 and it will be having V1. It will be having kinetic energy and it will be having potential energy because it will be having at this location. And after that it will be having some other kinetic energy T2 and V2. So the overall kinetic energy, the sum here overall will be equal to here. Since at this location the T1 is 0 because there is no kinetic energy, the ball is at a rest, and this v1 is almost 0 because this is on the datum, so this part is 0, the initial part is 0, so 0 is equal to the new kinetic energies and the potential energy. If the football is actually, there is a movement in the game of the football, so if the ball is actually moving and then movement from one, let's say example this is the datum position, and somebody has hit it this football which is above this ground y1, and this is y2. Okay, so in that case there will be a t1 v1, they will not be 0, and this will be equal to this t2 v2, which will be the new location of the body. So the overall energy remains constant or it is conserved, and this is called as the conservation of energy. Okay, and this is explained through this bob only. When it bobs was at an initial location and then it comes to this location and then again it comes down to another location. The explanation is same as a football. Okay, this is one kind of a problem in which this is a collar which is supported by a spring, and as this collar moves downward the spring is stretched. Okay, or a vertical rod, this collar is moving on a vertical rod. So a spring attached to the collar has an undeflected length of 4 inches and a constant of this. This is the spring constant. If the collar is released from rest, find its velocity after it has moved to 6 inches. That means to a position 2. So we will see and solve for the potential energy and kinetic energy since it is moving and moving from a height. Since initial kinetic energy is 0, so what will be the spring potential? This is calculated like this. This is spring constant 8 inches minus 4 inches. Why minus 4 inches? Because undeflected length is 4 inches. So deflected length minus undeflected length will be 4 inches. Okay. This was the initial minus undeflected is 4 inches. And V1 is VE plus VG. Just a moment. So the this is the kinetic energies of the body. And let me again do this. So V1, at the initial position we have spring potential energy plus the potential energy due to gravity. Okay, so this, the potential energy due to gravity is, there is nothing such that mg is 0, um, and so the overall potential energy is this. Okay, T1 is 0. So further, the potential energy at location 2, so this will be half kx2 square. So we have calculated that and obtained this at this. What will be Vg? Vg will be W times weight times the distance here, which is 6 inch. And since this is moving in this direction, and so this, the potential energy here is negative. Okay, and what will be V2? V2 will be again the potential energy due to the spring energy and mg. So these two will be added together. Okay, and the overall value comes out to be this. What is the kinetic energy in this case? Since it is moving, so it will be having some kinetic energy at this location. So this will be half mv square. This comes out to be this. So further, we'll add this in a conservation of kind energy. The initial positions T1 plus V1, and this is T2 plus V2. So the overall uh, equation will be V2 equals to 4.91 feet per second. This is a unit of velocity. So if you see this properly, you will realize that there are two basic forces, F1 and F2, which are actually responsible for the potential energies. And the potential energy increases from 0 to certain value, and this increases with respect to the distance. So initially it has a potential energy of 4, it has a potential energy of 2 feet per lb, and which is actually due to the majorly due to this undeformed minus this 6 inches. So this was one kind of energy obtained through spring constant, and this was another kind of potential energy obtained from the new position, which is 10 the spring stretch minus the 4 the unstretched spring. So we have obtained this kind of energy. So such problems are will be there, in which we will be having a combination of potential and kinetic energies in together, and in that positions try to develop or try to use the expression for the conservation of energy, in which the overall energy is conserved. And remember that these are the two locations. There may be three locations also, like for example from point 1 to 2, and there may be some another point 3. So in the third location also there may be, this will be equal to T3 plus P3. That will be third location, but in any case the energy will always be conserved. So we will solve another problem of this. This is another problem, and this is something we have seen. A roller coaster ride is there through this car, and this is moving on this path. This is a curvature A to B. C to D is also curvature. However, B to C is a straight line. Okay, the radius is given 40. The car and its occupant's total weight is given. Point A with a practically no velocity, this is at rest, then drops freely along a track. That means no external forces there, only the force component through the W. That means the weight. Determine normal force exerted by the track on the car at point D. Find the normal force. Okay, and air resistance, all these things are negligible. So we'll use first of all, we'll try to make a datum. As I've always said, this will be the potential energy releasing. This will be the release of potential energy from point A to point B. So we have fixed our datum at this location. Okay. So here the potential energy will be mg times this distance 90 plus 60, and at this location the potential energy will be 0. Okay. So we will find or use the conservation of energy principle. The kinetic energies and the potential energies at this location, and the kinetic energies, potential energies at these two locations. So Ta is 0 initially. It is written here that the movement is 0. Ta is 0, velocity is 0. What about Va? Va is W times Ya, which is 90 plus 60. And what is Td? Td is half mvd square. Now we do not know Vd till now. And what is Vd? Vd is a potential energy. So this was the velocity actually. Okay. What is the potential energy at D? This is 0 because the height is 0. We have taken this as a datum, height is 0. We'll put this in equation and solve for velocity at D. So the velocity comes out to be 98 feet per second. Looks very simple. Is it simple? It is simple, that much only. If you take or divide your problems in simpler steps, like in this case, we have calculated this optionally TA, VA, TD, VD. So we have calculated this in steps. We have divided our problem in steps. So we will be able to solve this very easily as we have seen. In the another case, FBD and KD at a point D. Um, so at this point D, we'll be having weight and ND will be normalizing it. So what will be the KD kinetic diagram? This will be the tangential force of this curve, tangential, and this will be normal force or normal component. Okay. So using the Newton's second law of motion, we will be able to find the ND, that is the normal force at D, using this expression. So overall force will be ND minus W equal to M times AN. AN expression we already know, V square by R. We'll solve for ND and we'll be able to get the ND. So this will be the normal force required at this location to safely come from that point to this 0 point. Remember that the ND should be there. If the ND is not there and the ND value is 0, that means that this this car will actually go flying through this and it will not be able to hold its position or not be able to hold its path. So it's important that the ND should be having some positive value so that it will be able to hold the car and it will make the occupants safe while coming down. What happens to the normal force if we include friction? Now this is very important and something tricky also. If we include friction, what will happen to ND? Will it get larger, smaller, or it stays the same? See, before we do that, let's see what the friction will do. Friction will reduce the energy. Friction will be acting against the movement of this car. So friction will actually reduce the energy. So ND will get smaller because the overall energy that is coming from here will be reduced. The work done by this will be reduced. So since the work done by this will be reduced, so ND will get smaller and smaller as it comes down towards here. Okay, what will be the other case? We move from point A higher. What does that mean? What happens to the normal force if at D we move point A higher. If we move this point A higher, there will be more potential energy. The potential energy will be more. That means you require more ND to be here. If you increase the potential energy, the car will come through a larger force. So you require more ND to make this car stick to this location. You require more ND. That means more normal force. So ND will be larger. And the radius is smaller. That means this radius, I think. This R, what happens at D? The radius smaller, ND gets larger, ND gets smaller, or ND stays the same. So ND gets larger in that case. So I request you to give this a thought. Okay, like the way we are explaining to you, you should also give some thought, like give a thought that why ND is smaller if you include the friction. As I told you, when it will go down, it will reduce the work done by this movement. And since the work done is reduced, here it will come at a reduced pace. So ND will be very smaller. And in a similar way, you have to ask the question why the ND is larger and why the ND is larger when the radius is smaller. These questions should be asked, and some other problems like that will be there in which such questions um, can be expected to come. So I hope this would be informative to you at some point in time, and this will be helpful to you to solve some of the other problems given in the assignment. And in the next lecture, we'll be discussing about impulse momentum equations, and they will be also used to solve the dynamics problem. So I'll take a leave from you. Thank you.